Read down sum number 8. Read it? Look. We have a network of 5 capacitors C1, C2, C3, C4 and C5 which are interconnected as shown in the diagram. Now we are asked to find out equivalent capacitance between points A and B. Correct? Here my dears, between points A and B, you cannot take any connection directly only as parallel connection. You cannot take any connection directly as series connection. Then how to find out equivalent capacitance? Then we need to take help of another circuit, another network, another concept. But that network you are going to study in the forthcoming chapter, that is in chapter number 3. It is about Wheatstone bridge. There was a fellow in physics with name Mr. Charles Wheatstone. He had prepared this network. So in his regards, we call that network as Wheatstone bridge. Now actually it is consisting of 5 resistors. Instead of capacitor, you may connect their resistor. Now what is electrical resistance? What is resistor? Everything you will be taught in chapter number 3. We will study that article very nicely in complete detail. But at present you just remember one condition which we are going to obtain actually in chapter number 3. What is that condition I am showing you? Given Wheatstone bridge has 2 arms, 2 branches you can say, 2 arms. And if you take ratio of resistances in one arm, and if it comes out to be equal to ratio of resistances in another arm in the direction of electric current, then if these 2 ratios are coming out to be equal, then that Wheatstone bridge is said to be in the balanced condition. And in that balanced condition, there is no current flowing through this 5th component, and if there is no current here in this branch, you may discard it, you may remove that component. It does not make any effect on the working of the network. Okay? Here instead of resistances, we have got capacitances, but the method remains same. How to check the balance condition of a Wheatstone bridge? I am showing you. This is one arm of a Wheatstone bridge. Look here this way. Correct? This is one arm of a Wheatstone bridge. This is another arm of a Wheatstone bridge. And this is the 5th component which is connected between these 2 points. Now here how to check the balance condition? You should check this way. This capacitance divided by this capacitance should come out to be equal to this capacitance divided by this capacitance. If it is so, it is said to be in the balance condition, and then you may remove this. Look, here it is 1 upon 3 and here also 2 upon 6. 2 upon 6 is nothing but 1 upon 3. So this upon this is really equal to this upon this. So present Wheatstone bridge is in the balance condition. If it is in the balance condition, you may remove this component. Why? Because in this case, when we connect here battery across points A and B, these 2 points remain at the same potential. If these 2 points remain at the same potential, then these 2 plates of this capacitor does not get charge. Okay? If these 2 plates do not get any charge, then it remains chargeless, and if any capacitor in any network is not getting charged up, then you may remove it, no problem. It does not affect the working of the network. Okay? So you may remove this capacitor, and once you remove it, then remaining part of the network will appear like this. Simply I have removed this 5th capacitance, come on. The remaining part I have drawn as it is. And now tell me, in this upper branch, how do you find C1 and C2? They are connected one after another. One after another means in series. Remove series connection of these 2 capacitors and place equivalent capacitance. Let it be C6. After C5, if you require symbol of capacitance, you must adopt this symbol C6. Similarly, in the lower branch, what do you find? the series connection of C3 and C4. Great. Come on. Remove this series connection also and just place an equivalent capacitance. Let it be C7. Okay. Fine. Now tell me, what is C6? It is equivalent capacitance of these two capacitances connected in series. Equivalent capacitance in case of series connection of two capacitances. What did I tell you to remember in words? Multiplication upon addition. Multiplication upon addition. Come on. C1 into C2 divided by C1 plus C2. But the values are 1 and 3. So I just multiply 1 into 3 divided by 1 plus 3. Multiplication divided by addition. Okay. This comes out to be 3 by 4 microfarad. Similarly, what is C7? Equivalent capacitance of two capacitances connected in series. Come on, C3 and C4 with the values 2 microfarad and 6 microfarad. Come on, two capacitances connected in series. What is equivalent in words? Multiplication upon addition. 2 into 6 divided by 2 plus 6. 2 into 6 divided by 2 plus 6. So altogether it is 12 by 8, which is 4 3s are 12, 4 2s are 8, so 3 by 2 microfarad. Now tell me, they have asked actually equivalent capacitance between these 2 points, correct? Now you can find here in this network, these two capacitors are connected in parallel between points A and B. And what is law of parallel connection of capacitors? Equivalent capacitance should be equal to summation of individual capacitances. So if equivalent capacitance between points A and B is CAB, then it should be equal to summation of these two values, that is C6 plus C7. C6 plus C7. What is C6? It is 3 by 4 plus C7 is 3 by 2. 3 by 4 plus 3 by 2, it is 9 by 4, that many microfarad. 9 by 4 microfarad. Okay. How is this Western bridge constructed and why it is said to be in the balanced condition? In this condition where you are finding ratio of two values in the two arms is equal, then why it is said to be in the balanced condition? That everything we will study very much in detail. Just have faith in me, we will definitely study in chapter number 3. Okay. But at present we are using that condition over here. This is then equivalent Western bridge, you can say, in terms of capacitors. There also we can just use that condition. If ratio of these two values comes out to be ratio of these two values, it is said to be in the balanced condition. Right now that condition is satisfied. 1 upon 3 is just equal to 2 upon 6. Okay. You may think of this way also. Look, this upon this, you may take this upon this. 1 upon 2 will be equal to 3 upon 6. 1 upon 2 will be equal to 3 upon 6, correct? So in any case, this Western bridge is in the balanced condition. So you may remove this because this capacitor does not get charged up. Okay. If any capacitor remains chargeless in any network, you may simply remove it, no problem. It does not affect the working of the network. Once you remove this, then the remaining part of the network I have shown here. In the upper branch, there is series connection of these two, and what is equivalent? Multiplication upon addition. That's what I am finding here, C6. And similarly, these two are also said to be in series in the lower branch. Let their equivalent be C7, again multiplication upon addition. 2 into 6 upon 2 plus 6. Simplify. And now tell me, between points A and B, how to find these two capacitances connected in parallel? So simply addition. Come on, C6 plus C7, that is this plus this, correct? And that addition comes out to be 9 by 4 microfarad. Okay, fine. Come on, my dears, we proceed further. Kindly read the statement of sum number 9. Have you read it? Look, my dears, here in this circuit, a special type of key is used which is called two-way key. That key is this. Why it is called two-way key? Because using this key, you can have connection in two different ways. One is the connection between these 2 points, that is one way. Another way of connecting these 2 points it is from here to here, correct? So you can just change the position of that key. Instead of connecting these 2 points, you may connect these 2 points also. So there are 2 ways of connection possible, that's why we call it two-way key. Fine. Initially connection is made between these 2 points where battery is connected across this capacitor. At that time this capacitor is not there in the circuit because there is no connection between these 2 points. So this capacitor is not present in the circuit, okay. So only this capacitor will get charged up, and so electrostatic potential energy will be stored in the electric field in the region between these 2 plates of this capacitor, okay. At that time there is no energy stored in this capacitor, okay. So initially what is the total potential energy? Let it be capital U. As such you can write U equals to U1 plus U2, U equals to U1 plus U2, but U2 will be 0 because this battery is not connected with this capacitor, so this capacitor will not get charged up, correct. So U equals to U1 plus 0, U equals to U1 plus 0, that is U equals to U1, and that U or U1 you can write this way, 1 by 2 CV square, correct, formula of electrostatic potential energy. Now 1 by 2, C is 900 picofarad, convert it into farad, multiply by 10 raised to minus 12. What about V? Potential difference between these 2 terminals of this battery is given to you 100 volt, make it just square. And now simplify, answer is 4.5 into 10 raised to minus 6, that many joule, correct. But that energy is stored only in the first capacitor, so you may write here U1 also, no problem, U equals to U1, correct. Now finally what we do, we disconnect these 2 points, and instead of just having connection between these 2 points, now the same key is employed to make connection between these 2 points, okay. So we just change the position of that key, and now as soon as this point is connected here, you can see battery is removed from the circuit, and this charged capacitor is connected in parallel across another capacitor having same capacitance, correct. This capacitor, when it is connected, it was initially chargeless. Now this charged capacitor is connected in parallel with another capacitor having same capacitance. Now in one such a problem, you had already solved this problem earlier in the MCQ number 8 in the exercise. You had one charged capacitor, and then after removing battery, you had connected the charged capacitor with another capacitor in parallel having same capacitors, and in that case the energy stored in one capacitor was U by 4. In that MCQ number 8 you can refer, its answer was U by 4, but they had asked energy stored in one capacitor. Here they have asked energy stored in both the capacitors, that is energy stored in entire system, let it be U dash. When I am putting dash, you must understand it is final condition, so it should be U1 dash plus U2 dash, but for each capacitor energy stored is U by 4. So I am writing here also U by 4, here also U by 4, correct. Addition will be U by 2, U by 2, that is this divided by 2, so this divided by 2, it will be 2.25 into 10 raised to minus 6, that many joule, correct. Just read the question carefully. If they ask energy stored in one capacitor, you may write U by 4, but energy stored in both the capacitors in the entire system in this case, then you must write U by 4 multiplied by 2, that is U by 2, correct, fine. Now kindly read the statement of sum number 10. Read it, come on. We are given a network of 4 capacitors having capacitances 10 microfarad each, okay. C1 equals to C2 equals to C3 equals to C4 equals to 10 microfarad. We are asked to find out 2 things. First, equivalent capacitance of this network between points A and B. Second, charge on each capacitor. Let us find out. If you move in this branch, look this way, then These 1, 2, 3 capacitors are found to be connected one after another, that is in series. Remove that series connection and just replace it by its equivalent capacitance, let it be C5. Okay? So what I have done in the next figure, instead of showing this entire series connection, I have simply replace it by single capacitor having equivalent capacitance C5, which is equivalent to series connection of these 3 capacitors. Okay, fine. Remaining part of the network I have shown as it is, no change. Now tell me, what is C5? It is equivalent capacitance of a series connection of identical capacitors. And in case of series connection of identical capacitors, what is the equivalent capacitance in words? Remember, single divided by number. Single divided by number. Single, it is C suppose, and all these 3 values are equal, let it be C divided by number. Number is 1, 2, 3. So I am writing C by 3. Single divided by number. Single value is 10 microfarad divided by 3. And now tell me, what do you find between points A and B? Parallel connection of C4 and C5. Parallel connection of C4 and C5. Then what is equivalent? Simply summation of C4 and C5, that is C4 plus C5. C4 plus C5, correct? Equivalent capacitance in case of parallel connection of capacitors is simply addition of individual capacitances. Come on, C4 is 10 microfarad. C5 we have found out it is 10 by 3. 10 plus 10 by 3 comes out to be 40 by 3, that many microfarad. And now they have asked charge on each capacitor. For C5, tell me, the potential difference across its plates is 500 volt, let it be V5, and the charge stored in this capacitor, let it be Q5. Then don't you know formula? Q equals to C into V. Q equals to C into V. Instead of Q I am putting Q5, instead of C I am putting C5, instead of V I am putting V5, correct? Now what is C5? C5 is 10 by 3 microfarad. 10 by 3 microfarad converted into farad multiplied 10 raised to minus 6. What do you mean by V5? Potential difference across the plates of 5th capacitor. Come on, potential difference across these 2 plates. It is nothing but potential difference across the terminal voltage of this battery, and it is 500 volt. Because the components are connected in parallel, potential differences across them must be equal. So potential difference across the plates of this capacitor should be equal to terminal voltage of this battery, which is right now 500 volt. So this voltage is 500 volt. Okay. Simplify, answer is 1.667 into 10 raised to minus 3, that many coulomb. And just recall that fact, in case of series connection of capacitors, remember whatever is the charge on equivalent capacitor, same is the charge in each capacitor connected in that series connection. So this C5 is equivalent to these 3 connected in series. So whatever is the charge in this capacitor, same should be charged in these all capacitors also, correct? So mathematically you can say Q1 equals to Q2 equals to Q3 equals to Q5. Here it is. Q1 equals to Q2 equals to Q3 equals to Q5. I just repeat, charge on equivalent capacitor in case of series connection is equal to charge in each individual capacitor in that connection. So this C5 is equivalent to these 3 connected in series. So whatever is the charge on this capacitor, same should be charged on this, same should be charged on this, same should be charged on this, correct? Mathematically, Q1 equals to Q2 equals to Q3 equals to Q5. Q1 equals to Q2 equals to Q3 equals to Q5. But what is the value of Q5? You have found out 1.667 into 10 raised to minus 3, that many coulomb, correct? What about this capacitor? Potential difference across this capacitor is 500 volt, and if charge is Q4, then according to formula Q equals to C into V, you may write Q4 equals to C4 into V4, correct? What is C4? C4 is given to you 10 microfarad. C4 is 10 microfarad, converted into farad multiplied by 10 raised to minus 6. What about V4? Potential difference across C4. Potential difference across C4, it is nothing but 500 volt. So this is the value 500 volt. Simplify, answer is 5 into 10 raised to minus 3, that many coulomb. So we had to find charge on each capacitor, that's what we have already done. Q1, Q2, Q3, Q4, correct? We have found out charge on each capacitor. Kindly read now number 11. Read it? Come on. We are given this sort of network of 4 capacitors in which we have to find equivalent capacitance between points A and B. In order to solve such problems, I am just showing you the easiest way. Whichever 2 points in the circuit you find connected directly by some wire, there is no component between them, then you may take them as same point. For example, these 2 points, you can see they are connected directly by a wire. There is no component here between these 2 points in this branch. So those 2 points you must treat them as same point. If this is the point they have given as point A in the statement, then this point also you must take as point A, because they are connected directly by a wire. Similarly, in the statement you will find this point is given as point B, but you can see these 2 points are connected directly by a wire, then you can take this also as point B. Okay? If you treat the sum this way, then you will find to simplify very easy. Look, now if I move in this branch, look this way, then I find that these 2 capacitors are connected in series. Remove that series connection, replace it by its equivalent capacitance, let it be C5. So just remove this much part, replace it by its equivalent capacitance C5. I have done it here. Right? Now how to find out equivalent capacitance of series connection of identical capacitors? Just now I told you, single divided by number. These 2 they have given same value, C2 and C3 are having same values. So these 2 are identical capacitors connected in series. What is equivalent capacitance? Single divided by number. Single is 2 microfarad, divided by number is also 2, 1 and 2, 2 upon 2, that is 1 microfarad, correct? So this C5 is 1 microfarad. And now tell me, this series connection is replaced by C5. Now this is equivalent to this network. This is equivalent to this network. How? You can check. 2 plates of C1 are connected with points A and B. Here also 2 plates of C1 are connected with points A and B. 2 plates of C5 are connected with points A and B. 2 plates of C5 are connected with points A and B. 2 plates of C4 are connected with points A and B. 2 plates of C4 are also connected with points A and B, correct? So whether you find out equivalent capacitance between points A and B here or here, it will make no difference, because this network is equivalent to this network, correct? But here between these 2 points we can find that these 3 capacitors are connected in parallel. How? If you connect here positive terminal of the battery, you will connect negative terminal of the battery over here, correct? Now tell me, this is positive, so these 3 plates, these 3 upper plates will lose the electrons and they will be just going towards this positive terminal of the battery, and after losing electrons these plates will become positive. Similarly, these 3 lower plates will become negative. Tell me, I told you, if interconnected plates have like charge, that is same polarity of the charge, then the connection is nothing but parallel connection. These 3 plates are interconnected here at point A, they all have positive charge. These 3 lower plates are connected at point B, they all have negative charge. So if the interconnected plates have same polarity of the charge, then the type of connection is parallel connection. And because these 3 are connected in parallel, what is the law of parallel connection of capacitors? Simply addition of individual capacitances. Come on, C1 plus C5 plus C4 will be equivalent capacitance between points A and B. So I am writing CAB equals to C1 plus C5 plus C4. Come on, C1 and C4 they have given. C1 and C4 they have given 1 microfarad. C5 we have found out 1 microfarad. 1 plus 1 plus 1, that is 3 microfarad. Simple. Kindly read the statement of sum number 12. Read it. Look. For the present arrangement of 4 parallel plates, what is the equivalent capacitance between points A and B? That is what we have to find out. All the 4 plates are identical in all respects. They got same plate area, same surface area, and let it be capital A. If perpendicular separation between 2 consecutive parallel plates is small d, what is the capacitance? C equals to epsilon 0 A upon D. Okay. Now we are asked to find out equivalent capacitance between points A and B. Come on. Just for the sake of easy understanding, I have shown the same color of the plates as is shown here, same way it is shown here, and this network is now equivalent to this network. How I am showing you? Come on. I told you that the plates which are coming at the 2 endpoints, correct? There is no plate above this, there is no plate below this. Their order will come only once. Their order will come only once. Plate number will come here only one time, here. Plate number 4 also will come only one time. But the intermediate plates have upper and lower face which are getting charged. Then we have to consider both the faces, upper also, lower also. So there are 2 faces of upper and lower, 2 faces of plate number 2, upper and lower. And so plate number 2 will come twice. Look here. Plate number 2 is coming twice. Similarly, we are going to consider upper and lower face of plate number 3. That's why plate number 3 will come twice. Look, plate number 3 is also coming twice. Okay, fine. And now how is this equivalent to this? I am showing you. Plate numbers 1 and 4, they are interconnected. Plate numbers 1 and 4 are interconnected. Plate number 1 and 4, they are interconnected. Correct? Come on. Opposite to plate number 1, what is it? Upper face of plate number 2. Opposite of plate number 1, what is it? Upper face of plate number 2. Opposite to lower face of plate number 2 is upper face of plate number 3. Opposite to lower face of plate number 2 is the upper face of plate number 3. Opposite to lower face of plate number 3, there is a plate number 4. Opposite to lower face of plate number 3, there is plate number 4. And which plates are connected at point A? Only plate number 2, upper and lower faces, correct? Come on, at point A, upper and lower face of plate number 2 are connected. At point B, which plates are connected? Only plate number 3. Of course, it's upper and lower face. So, upper and lower face of plate number 3 are connected at point B. In all respects, this circuit or this arrangement is equivalent to this arrangement. Correct? So, whether you find out equivalent capacitance between points A and B here or between points A and B here, it will make no difference. Correct? Now, here you can see these 2 capacitors which are identical because they both have same capacitance C each. They are in series, correct? And remove that series connection, replace it by its equivalent capacitance. In case of series connection of identical capacitors, what is equivalent? Single divided by number. Single is C, number is 1 and 2. Okay, single divided by number. So replace this entire series connection by its equivalent, which is C by 2. This lower capacitors I have shown as it is. Correct? Now between points A and B, we find equivalent. We find that these 2 capacitors are connected in parallel. Because these 2 capacitors are connected in parallel, what is the equivalent capacitance between points A and B? Come on, simply addition. C plus C by 2. C plus C by 2. That is 3C by 2. Correct? That is 3 by 2 into C. 3 by 2 into C. What is C? Epsilon 0 A upon D. Correct? Fine. I hope you have understood because I have not changed the colors also. Correct? Come on, now read this statement of number 13. Read it? Come on. Again we have an arrangement of 4 identical parallel plates. Plate number 1, 2, 3 and 4. Each plate has surface area capital A, perpendicular distance between two consecutive parallel plates is small d, then the capacitance formed between such two plates is C equals to epsilon 0 A upon D. Fine. We have to find out right now equivalent capacitance between these 2 points A and B. Let us find out. I told you whichever plates are at the end points, they will come only one time in the equivalent arrangement. There is no plate above this, there is no plate below this, so their order will come only one time. Plate number 1, you can see it is coming only one time. Plate number 4 is coming only one time. But the intermediate plates, their upper and lower faces we have to consider. So their order will come twice. Plate number 2, you can see it comes twice. Plate number 3 also comes twice. Correct? How is this arrangement equivalent to this? I am showing you. Upper and lower faces of plate number 2 are connected with point A. Upper and lower faces of plate number 2 are connected at point A. Correct? The plate number 4 is connected with point B. Plate number 4 is connected with point B. Correct? Opposite to plate number 1, there is upper face of plate number 2. Opposite to plate number 1, there is upper face of plate number 2. Opposite to lower face of plate number 2, there is upper face of plate number 3. Opposite to lower face of plate number 2, there is upper face of plate number 3. And opposite to lower face of plate number 3, there is plate number 4. Opposite to lower face of plate number 3, there is plate number 4. Correct? So in all respects, this arrangement is quite equivalent to this arrangement. So whether you find out equivalent capacitance between points A and B here or between these 2 points here will make no difference. Tell me these 2 capacitors you will find in parallel between points A and M. For parallel connection of capacitors, what is equivalent capacitance? Simply addition, that is C plus C, that is 2C. Replace this parallel connection by its equivalent capacitance, which is 2C between points A and M. Correct? Between points M and B, this capacitance C I have kept as it is. Okay? Now tell me, between these 2 points, how do you find this connection? That is series connection, one after another, that is series connection. And if you have got series connection of 2 capacitors, what is equivalent capacitance? Multiplication divided by addition. So 2C into C upon 2C plus C. 2C into C upon 2C plus C. This 2C into C I have kept as it is in the numerator, but in the denominator 2C plus C, that is 3C. 1C is getting cancelled. So now it is 2C by 3. 2C by 3, that is 2 by 3 into C. What is C? Epsilon 0 A upon D. Right? Here it is 2 by 3. Here it is 3 by 2. Take care. Here series connection of 2 identical capacitors is connected in parallel with third capacitor, and here parallel connection of 2 capacitors is connected in series with the third capacitor. That is the difference. Okay.